In this next module, we're going to dive right into the logistic regression model. We've talked about when you have binary or categorical outcomes, that is when you're looking at proportions. We've talked about some statistical tests when you don't want to adjust for anything that you can use. So this is like the risk difference, relative risk, the chi-square test, the McNamara's chi-square test. So we talked about those. But what about when you want to do a regression analysis when you have a binary or categorical outcome? In that case, you're going to be using logistic regression, which we're going to talk about in this module. I want to just give you a little overview of logistic regression. So to remind you, when we did linear regression, the model looked like the following. We were predicting the value of some continuous outcome variable, call it y, as a function of x. Here's a simple linear regression model. We have the intercept alpha and beta is our slope. So that was the simple linear regression model. In the multivariate regression model, we can add some additional betas and x's, additional predictors. That makes it then a plane or a higher dimension thing. But essentially, we're fitting lines, linear regression. Logistic regression actually isn't that different. The right-hand side of the equation is identical in logistic regression. So it's going to look something like this. There's a linear combination of betas and x's, risk factors. It looks exactly the same, and everything's going to be set up exactly the same in terms of defining the predictors of the model. You can put binary predictors in, you can put continuous, you can put categorical, you can do dummy coding. All of that is the same as with linear regression. What's different in logistic regression is the left-hand side of the equation. We are no longer modeling yi, the outcome variable, directly. Rather, we're going to be modeling a transformation of the outcome variable. In the case of logistic regression, we're going to be modeling the log odds of the outcome. And I know that sounds terrible. That's called a logit function. But don't worry, I'll explain why in a minute. We're going to be modeling this logit function, the log odds of the outcome. That's our outcome variable. We're going to be modeling that as a line, though, as an alpha plus a beta x, an intercept and a slope. Because we've made this transformation, the beta is just slightly more complicated to interpret than the beta from linear regression. So for linear regression, the beta was just the slope. It's as x goes up by 1 unit, how much does y go up? So there was a direct interpretation. It's just slightly more tricky to interpret the betas from logistic regression, but actually it's not terrible, because the betas from logistic regression, if you exponentiate them, what it gives you out is the odds ratio. And I referred to, in the second week of the course, we talked a lot about odds ratios, and I told you, hey, logistic regression spits out odds ratios, and this is where it comes from. The betas can be directly interpreted as odds ratios just by exponentiating, and the reason there's an exponential involved is because our outcome variable involves a natural log. So this is just the overview of where we're going this. Just keep in mind that the right-hand side of the equation is the same as with linear regression. So we're still fitting a line. It's just we're fitting the outcome variable. There's something trickier going on. Let me start here with a simple example using that example data set on my Stanford students that I've been using since the beginning of the course. One of the questions I asked my Stanford students is whether or not they consider themselves to be book smart or street smart. This is a binary variable. Book smart, if the variable is equal to 1, that means that they consider themselves book smart. If the variable is equal to 0, the way I've coded it, that means that they consider themselves to be street smart. So you can see that this is the book smart group over here, and this is the street smart group over here. And just as an aside, I've been asking this question to lots of Stanford students just for fun over the years, and it generally comes out about 80% of my Stanford students consider themselves to be book smart, and about 20% consider themselves to be street smart, and that was indeed the case in this little practice data set. It's right around 80%. I wondered if book smart students spent more time on homework, were more studious than street smart students. And so I wanted to look at the variable homework in the number of hours per week that they spent on homework. That's another question that I had asked these students. And we can look at that here, and I've done this, I've looked at this graphically here. So I'm graphing my predictor variable is just a binary, a yes, no, book smart or not. And my outcome variable here is homework in the number of hours per week. And now surprisingly, the students who consider themselves book smart, as you can see from this graphic here, actually on average do slightly less homework than the students who consider themselves street smart for whatever reason. So it went kind of in the opposite direction from what I might have expected. This analysis, this graphic that I'm showing you here, actually coincides with a linear regression. So the way I've set up the problem now is I've got a binary predictor variable and a continuous outcome variable, homework. And we could model this with a linear regression using what we talked about last week. When we have a binary predictor, it's a very simple linear regression, right? That line is just you connect the mean for the street smart group with the mean for the book smart group. And if you connect 2 points with a line, that defines a line. And so we end up with a very simple line. So we could answer this question, look at this question in this data set with a linear regression, or even a t-test, which of course is a special case of a linear regression. This is cross-sectional data, however. So I've happened to pick, just for the purposes of illustration, for this slide, to put book smart as the x variable as the predictor and homework as the outcome variable. But because this is cross-sectional data, I could flip that. I could ask not whether or not whether you classify yourself as book smart predicts the amount of homework you would do, but I could ask it the other way. Does the amount of homework you do, amount of time you spend on homework, predict whether or not you consider yourself book smart? So I'm just going to flip the x and y variables. So here's the graphic when I flip the x and y variables. So now my x, my predictor variable, is continuous, the number of hours spent on homework per week, and my outcome variable is this binary, this yes, no. 0 is street smart, 1 is book smart. We've got a new graphic, and we could try to fit a line to these data. But look what happens when I try to fit a line to these data. Notice that all of my outcomes are either all 1 or all 0, so you just get these 2 stripes, and it doesn't seem optimal to try to fit a line. I did fit a line to these data. You can do it. This is a linear regression line, so I fit the best fit line to these data. But you can see that if you look at this picture, it doesn't really look like that line fits the data very well, right? I mean, when we were doing linear regression last week, we had these scatter plots, and we were trying to find the line that was kind of very close to all those dots. Well, this line does, even you can fit it, but it doesn't look very close to all of those dots. It doesn't look like a very good fit. So a linear regression model is not optimal here. Well, what do? Again, I told you we're still going to want to fit lines here. So how can we still fit a line, but do something other than linear regression? What could we do? So what we could do here is to transform the outcome variable. Again, I still want to fit a line ultimately, but I don't want a 0, 1 variable as my outcome, because a 0, 1 variable just doesn't fit well to a line. It has only 2 possible values. So what could I do? How could I transform that binary, that 0, 1 variable, into something that better fits a line? Well, here's one thing. This is just a starting point, because we're going to go further with this, but let's just start with some simple thing that we can do. So recognize that instead of modeling it as a yes, no, a 0, 1, what if we could somehow model it as a probability? A probability, as you know, is a value that ranges from 0 to 1, but it can take on any value between 0 and 1. So we would do a little bit better. We would put in all these values between 0 and 1 back into play if somehow we could model this as we could make the outcome variable the probability of being book smart rather than yes, no, you are book smart. Just looking at the data here, you can see, well, that's not immediately obvious how you would do it. In fact, we're going to do something called the logit, which is a function of the probability. And in fact, what the computer is going to do is do a little algorithm involving some calculus to calculate the probability or the logit. But we can kind of approximate it just actually looking at the data. And I think this is the best way to understand it. So if I wanted to get a probability here rather than a 0, 1 variable, imagine I did the following. What if I just, to get a probability, I'm going to have to look at more than one person. I'm going to have to look at a group of people. So what if I kind of arbitrarily looked at a group of people. Let's just pick, say, the 10 people with the lowest amount of homework time per week. Notice that these little red dots here, actually some of these dots represent more than one person, because there were a lot of people who had tied values. They selected the same number of homework and they also called themselves book smart, for example. So that each of these dots may represent more than one person. So imagine that this what I've put in this box here represents 10 people. I could look at say the 10 people with the lowest amount of homework time, putting in the lowest amount of homework time, and I could count up how many of them called themselves book smart and how many of them called themselves street smart. And I could calculate a proportion, a percentage, a probability. So let's say, I'm just making this up, but let's say when I calculate that, again, since some of these dots are overlapping, I can't do it exactly, but from the graphic, but let's say I count up and I find that among those doing the least amount of homework, let's say that 90% of them, again I'm just making this up, let's say 90% of that 10, 9 out of 10, considered themselves book smart rather than street smart. Now I've got a probability rather than a 0-1. And I could do this for the next group of 10, the next highest in homework. Maybe in the next group the probability is, again I'm just making this up, is 85%, and I can't tell because again these dots are overlapping. Maybe that comes out to be 85%, but I could go along and I could group people. I have to group people in order to be able to get a percentage of probability, but I could come up with some probabilities. And of course the probabilities I come up with are going to depend exactly on how I group them. But just realize that the grouping is just for the purposes of illustration. When you actually do this with calculus, you don't have to make any arbitrary groupings. Of course, we won't go through the calculus here, but the computer does that for you. So if I could get that probability, now I can make a graphic, which is my predictor variable is the number of hours of homework per week, the continuous variable. Now my outcome variable is a probability, a number that ranges between 0 and 1. I have fewer dots on this graphic. I'm going to just for now talk about the graphic on the left side, this 10 groups. I notice I have fewer dots on that graphic. None of these dots are overlapping anymore. So I actually have my previous graphic represented 48 people. This graphic only represents 10 observations. I divided those 48 people up into roughly even groups of 10 groups of, somewhere between about 4 or 5 per group. And I got those percentages and I plotted them here. What you notice is this is much more amenable, this scatter plot, to fitting a line. Right now we've got dots all around the range, and you can imagine actually fitting a meaningful line to those dots. As I mentioned, this is just for the purposes of graphing, just to show you the concept. And so it's arbitrary how I group people. So of course the graphic's going to look a little bit different depending on how I group people. So just to show you that I also divided it into 5 groups. There's 48 people, so this is roughly groups of 8, 9, or 10. And I calculated the proportion who considered themselves book smart, that probability, in each of those 5 groups, and I plotted it here. By the way, when I'm each of these groups, of course, has a range of homework values. I'm using the mean homework time for each group. That's what I'm putting in the plot here. So for example, the lowest homework group on this plot here, they had a mean homework time of just, maybe 30 minutes to an hour, and the proportion that considered themselves book smart was right about 78%. So I'm using the mean just for graphical purposes. But the picture looks a little different depending on how you group it, but you can get the idea. Now we've put back all the numbers between 0 and 1 into play. It makes much more sense to fit a line. But this is still limited, okay? So this is not, we're going to go further than that with this, because a probability is a number that's bounded between 0 and 1. So it's still a bounded quantity. You can't go lower than 0, you can't go higher than 1. The problem with that is, imagine when we fit a line, when you fit a line, theoretically, that line can go anywhere from the y value can go anywhere from negative infinity to positive infinity. So this is still not perfect. So what we're going to do is, instead of directly having the probability be the outcome variable, we're going to make a little transformation. So probability is bounded from 0 to 1. If I divide the probability, however, by 1 minus the probability, that, of course, is what we learned earlier is the odds. So divide the probability by the probability of something not happening, so the probability divided by 1 minus the probability, that's what we learned in week 2 of the course, is an odds. Why would I want to do that? Well, a probability can't be bigger than 1, but an odds can go from anywhere from 0 to positive infinity. The odds has no right-hand bound. So now we've put in all the positive real numbers back into play. We're still missing the negatives. How can we get the negatives back in? So here's where the natural log comes in. So if I then take the natural log of the odds, it turns out that when you take a natural log, any value that was below 1 now becomes a negative number. So this, the natural log of the odds, actually ranges from negative, can theoretically range from negative infinity to positive infinity. So now we've put all the numbers back into play. So now this is the most optimal for fitting a line. So the outcome variable for logistic regression, as I'd mentioned earlier, is actually going to be the natural log of the odds of the outcome. A little complicated, but it's for mathematical reasons that we choose that. And just to illustrate, I took the same groupings, 10 groups and 5 groups, where I had calculated the percent, the probability of being book smart in each of those groups, and I transformed that into a log odds. That is, I took the percentage divided by 1 minus the percentage, and then took the natural log of that number. This gives me some numbers like 0.5, 1.0, 1.5, 2.0. The log odds has no inherent meaning to me, but that's okay, because when we eventually we'll translate it back into something meaningful. But now this outcome variable is a number that could theoretically go anywhere from negative infinity to positive infinity. Makes it very nice for fitting a line. I'm graphing here the logit for each of these groups against, again, the mean homework time in each of those groups. And you could fit a line to that. And that's what we're doing in logistic regression. That's the line that we're fitting. So we're going to estimate an alpha and a beta, an intercept and a slope for that particular line. As I mentioned, the groupings here are completely arbitrary. When you actually do this in the computer, there's calculus going on, and so you're going to get the best alpha and the best beta. When I do this graphically, it's a little bit of an approximation. You can see that the line is slightly different when I group it into 10 groups than when I group it into 5 groups. These lines are slightly different. But we can actually kind of look at these graphics and just kind of visually approximate the equation of that line. So I'm going to do that now. This is not as good as doing the calculus in the computer, but it'll give us a little bit of an approximation, and I think is also good for illustrating what's actually going on here. So what is the equation of this line? There's 2 lines here, and we can kind of say the real line is going to be somewhere around these 2. So first of all, what's the intercept value? So if I just look at the graphic, my intercept for this line over on the left side is, I'm going to guess, about 1.6. You know, I'm just approximating here. And the intercept over for the line on the right-hand side of the page is maybe about 1.8. So let's just kind of call it that the equation for this line, again, if we're kind of saying there's one line here that we're trying to approximate, maybe it's around 1.7. I'm just making it somewhere in that ballpark, maybe around 1.7 is the intercept. How would I get the slopes of these lines? Just visually here, how could I approximate the slopes of these lines? So what's the slope? It's rise over run. So I could say, well, how much have I gone up in the y variable, and how much have I gone up in the x variable? So I can just kind of look at this as a triangle here and say, well, how far did I go? On the x-axis, I went from about 0 to 40. So the x change is about 40 here for this triangle. On the y end of things, yeah, if you kind of approximate, it's maybe going from about 0.3 maybe to 1.6. I'm going to just call it 1.3. So sorry, we go up 1.3 in the log odds. So the slope here is going to be rise over run, so 1.3 divided by 40, or approximately 0.03. So the slope here is about 0.03. For this line, we can use the same kind of logic. So for the x, we went over about 35 here. That's about 0 to 35. On the y end, we've gone up a little bit bigger, maybe about 1.8, from 1 to about 1.8. The slope then would be 1.8 divided by 35, which is about 0.05. So, you know, this somewhere, I'm going to approximate somewhere between 0.03 and 0.05. Let's call it 0.04. And of course, this is negative. I should emphasize here that this is a downward slope. We've gone down 1.3 or down 1.8 in y. So both of these slopes are negative. So on average, the slope's maybe somewhere around negative 0.04. This is just my graphical approximation, but that's what we're doing on logistic regression. That's the line we're fitting. Now I'm actually going to put the data in the computer and let the computer use the beautiful calculus to estimate this perfectly to get the actual best intercept and best beta slope that fits these data. And I'll show you that our approximation wasn't bad. Here's what the computer comes out with when it does what's called maximum likelihood estimation. This involves calculus. It gives us some maximum likelihood estimates. I'm not going to go into the details of maximum likelihood estimation. That's for another course, but this is just the way, using some calculus, that we're getting the best alpha and the best beta here, the best fit line. So when I do this on the computer, the intercept comes out to be just over 2, so just slightly different than what we got in our approximation. The slope came out to be right around negative 0.04, negative 0.039. So, and where did I get those in the output? Here's the estimate for the intercept, that's the alpha estimate. Here's the estimate for the beta, that's the estimate for the slope. Along with the alpha and the beta, we also get a p-value to tell us whether that alpha or beta is statistically different than 0. A beta of 0 would mean no association, same as it did with linear regression. So the intercept is clearly significantly different than 0. Again, that's not all that meaningful here because we wouldn't expect the intercept to be 0. However, the p-value for homework is not statistically significant. So as you might have guessed just looking at the picture, there isn't a strong association here. So it's not statistically different than 0. Probably meaning it doesn't look like there's a lot of evidence that homework and whether or not you consider yourself book smart are related. But here's the final model. The log odds of your log odds of being book smart or considering yourself book smart is equal to the intercept 2.12 minus the slope 0.039, and we would of course multiply that beta times the amount of homework. So this is a continuous predictor, so we would be multiplying the amount of homework for a particular person times that slope. What's this logistic regression equation useful for? So just like when we talked about linear regression, there's couple different potential functions here. So one thing is we could use the logistic regression equation model to try to do some kind of prediction. This is very useful in clinical applications because often we want to classify people as having a condition or not having a condition. That's a binary outcome. So if we're doing that kind of prediction, we would likely be using logistic regression. So we can try to come up with a set of predictors that predicts who's going to have a disease or not have a disease. So that's one of the functions of logistic regression, prediction. A second function of logistic regression, which is probably used even more often, is just to try to say, is a particular predictor, like homework, related to the outcome, in this case book smart or street smart, are those variables related? Is a treatment related to an outcome? And that's very useful in and of itself. And of course we can say, is that predictor, that treatment, related to the outcome after adjusting for potential confounders? So that's another very important use of the logistic regression model. I'm going to start by talking just briefly about the first of these aims, which is the prediction end of things. Again, here's the logistic regression model. We've modeled the outcome variable is the log odds of the outcome. We're modeling that as a line. Let me take that model that we just fit, and how would we actually apply it to make some predictions? So if you're somebody who does no homework per week, 0 hours of homework per week, you could plug in that value for homework of 0 into the model. You get that your predicted logit is 2.12. As I mentioned, most of us don't think in logits, so in a minute we're going to do something with that number to make it more interpretable. But if you did 10 hours per week of homework, you could plug in 10. The predicted logit there is 1.73. If you did 50 hours per week, the predicted logit is 0.17. So the more homework you do, the more the logit goes down. Well, I don't want to deal with a logit because a logit, I can't think in logits. However, we can get this, notice that there's a probability in there. What we want to get out is the predicted probability of the outcome, the predicted probability of considering yourself book smart in this case. I want to isolate this predicted probability. Well, it's actually not that hard to do, right? We've got one equation, one unknown. We can isolate that probability. So how do we do it? First thing that we're going to want to do is we're going to want to exponentiate both sides. So for example, the 0 hours per week, that person would be predicted to have a logit of 2.12. I can then exponentiate both sides of that equation. So that would tell me that the odds for somebody who does 0 homework per week is the exponential raised to 2.12. That value is 8.33 if you actually calculated it out. So e raised to 2.2 is 8.33. That's the odds for a person who does, the odds of being book smart for a person who does 0 hours per week of homework. Then we could exponentiate this 1.73. That will give me the odds for somebody who does 10 hours per week. That's 5.64. We could exponentiate the 0.17. That gives me the odds for somebody who does 50 hours per week. That comes out to be 1.19. So your odds of being book smart, again, goes down as you do more homework per week. Sort of the opposite of what you might expect. But of course, this is not statistically significant.